Thanks everyone for coming to my talk, and I will be talking about compatible triangulations. This is a joint work with Professor Anna Lubiu and myself. We are from University of Waterloo. So let's see first what do I mean by compatible triangulations. So I want to solve some computational problem where you are given two polygonal regions, that means polygons with holes, and I want the vertices to be labeled, and for each face the circular ordering of the vertices, the label of the vertices are the same. So here you have two polygonal regions, and I want to compute triangulations of both of these polygonal regions, and I want the resulting triangulations to be isomorphic. And sometimes you can do it, sometimes you cannot. So I want you, or I allow you to use Steiner points or some extra points so that you can always do it. And here is one example of for this particular polygonal regions where these tiny little dots are your Steiner points. And this problem is known under the name of joint triangulations or piecewise linear homeomorphisms of polygons. And there might be many other names. This is quite studied for a long time in the history of computational geometry and morphing. And I want to show you in one slide the motivation. So in the case of morphing or shape animation, you have a source and you want to reach a target. And if you want to transform from one to the other, you can find these isomorphic triangulations and find a linear morph between the source to the destination. Well, so what I am going to do in this presentation is to prove some variation of this compatible triangulation problem to be NP-hard, but first I want to discuss some related research and why this NP-hardness will be interesting. So the first idea was by Aronov et al. And they observed that if you are given two simple polygons, then you actually can decide in polynomial time that whether you can always find compatible triangulations or not, I mean for this particular input, without any Steiner points. And the idea is very simple. You just try every chord and you divide the problem into sub-problems and then test like recursively whether they have these compatible triangulations, and this is a very nice little dynamic programming that will give you a testing algorithm in polynomial time for 0 Steiner points. Well, so if you are allowed to have many Steiner points, they show that order n square Steiner points suffice to show you can always do it. So I want to briefly discuss how they did it. So you have these two simple polygons, you triangulate them independently like this, and then you consider a convex polygon. This is my convex polygon, and you put those chords inside these convex polygons, and you have some number of crossings, and it is straightforward. There are at most n squared of Steiner points there, and somehow you trace those chords back into the original polygons. Now, still you do not have quite a triangulation, you can have foregons, but that are still close enough, and you can triangulate those such that the resulting triangulations are isomorphic. So this is the idea of having a solution with n squared Steiner points. Well, it turns out that sometimes you need at least omega of n squared Steiner points, and these are two polygons here. And if you apply the same idea, you can have only this type of chords for the first one and this type in the second one, and if you overlap them, there will be at least roughly n squared intersection points. So n square is sometimes necessary, and later result shows improves on this. How they improve is Kranakis and Urrutia showed that order n plus r squared Steiner points suffice. R is of course the number of reflex vertices, and then Gupta and Wenger showed that you can actually approximate the number of Steiner points, and they gave a log n approximation. So, these were all for simple polygons. Now, what happens to the polygons with holes? They show that I think Babikov and others show that n square points are still sufficient to triangulate them isomorphically. And there is this another related research that came up, that if you have point holes, so if you think your holes as points, then you have point sets, and consider the polygon as just a bounding rectangle. Now, if you have this type of scenario, then still you can do it with n square Steiner points and triangulate the point set isomorphically, and sometimes you need at least n square points. Now, why I want you to show all these things is all this paper had one thing common, and probably you know what is that, is what is the complexity of minimizing the number of Steiner points. So, they all of them asked in the conclusion, we do not know the answer. So, in this presentation, I want to prove the NP hardness for a particular variant where you have this polygonal region, you want compatible triangulation, and you want to minimize the number of Steiner points. Well, so let us see how we did that. So, the reduction is from rectilinear monotone 3 set. It is planar, I just did not put that here, but the idea is you have a 3 set and you can draw the close to vertex graph in a planar fashion such that the vertices are boxes on a horizontal line, as you can see over x1, x2, x3, x4, and the clauses are either above or below, they are also boxes, and there is a vertical line between them if a clause contains a vertex. There is another restriction, that is why we call it monotone, is the clauses above the vertices, like the horizontal line, have all the positive variables, and the clauses below have all the negative variables. Well, so here is our rectilinear monotone 3 set. What are we going to do? We want to construct 2 polygons with holes, and we want to say that if we can triangulate them isomorphically with say k Steiner points, we can find the satisfiable assignment, truth value assignment for our set, and vice versa. So, first we do kind of transformation. Here, as you can see, the top edges I rotated them 45 degree, and the bottom I also rotated them 45 degree. I do not know yet what I am going to do, but here is what I am going to do. So, I take 2 copies of those and I thicken the edges a little bit. So, I want to construct polygons P1 and P2. These are my 2 polygons. They are exactly the same in this figure, but I will later modify that a little bit. And after I do that, I want to show, okay, if you can triangulate them isomorphically, then I can find, like with k Steiner points, then I can find a satisfying solution, and the other way. So, this is the overall idea. Well, now if you think about it, I am talking about Steiner points, and so far I did not talk about Steiner points in this reduction. So, I have to have some control of how many Steiner points I am going to put and where I am going to put. So, here is the key idea. So, if you have 2 polygons like this, I can claim that you need some Steiner points to compatibly triangulate them. Why? Look at this dent UDV. This is just a dent that is outward of the polygon, and the same dent UDV on the second polygon that is inward. Now, if you have a compatible triangulation without a Steiner points, then you have to have either the edge UV here or the edge that connects D to some vertex. Now, it happens that in the second polygon, either you cannot have a straight line visibility between U and V, or the point that you wanted to connect is actually not visible to D. So, if you have this type of scenario, then you need at least one Steiner point, and these ideas have been used to build some clause gadgets. So, we have these 2 polygons and these clause regions, and I take those and I put lots of dents, and there is a nice combinatorial argument to show you a lower bound that you need at least 5 Steiner points to compatibly triangulate them. Well, so then the other one direction becomes easy. So I claim that if I have 5 times the number of closed Steiner points, then I can actually find the satisfiable argument, satisfiable assignment. So how do I do that? Is you need for one clause at least 5 Steiner points, and this is how the variable gadget looks like, and the top clauses need some connection at the bottom points, and the bottom clauses need some connections to the top points, and you cannot have both of them simultaneously because there will be a crossing and that will raise a Steiner point, that is an extra Steiner point that I do not want to have. So this will give me a satisfying assignment. If these things comes from the top, I set it true, otherwise I set it false, and this argument shows that okay, you can actually satisfy all the clauses. And the other side is a bit construction that for all possible assignments of truth values, you can actually construct a corresponding isomorphic triangulations with 5 Steiner points, except for the case when you have all of them false, then you need 6. Okay, so this roughly tells how we did the hardness reduction, and what I really want to show you some open questions that are really interesting. The first one is we just know the problem is NP hard. We do not know whether the problem is NP complete. So this is one of those weird problems that we can't tell anything, but let us see what we can do in this case. We try to do some generalization of Tart's algorithm. So you know that planar graph drawing, the famous algorithm by Tarts, you have this convex polygon and you can put the other points inside, find the straight line drawing algorithm of the given graph. Now we have some similar scenario where you have the boundary that is concave, and you want to put your extra Steiner points and still find the positions such that everything is a straight line and nice. So we do not know whether there is any such generalization. There is, but they have some extra restrictions so that we could not use them. So one question is generalize Tart's algorithm to find planar straight line drawing within a non-convex boundary. And this is not the only candidate. There are other candidates that we do not know to be NP complete. So first the question here, you have a planar graph and you have for some vertices the location of them, and you want to extend that to a nice planar straight line drawing where B and C here you can choose where to place them, where A, C, A, E, D are already placed. So for this problem we do not know whether this is NP complete to decide or not. Well, so there is another nice question that I would like to ask. So we know that there is a dynamic programming to test whether you can triangulate 2 simple polygons with 0 Steiner points, but if I want to ask the minimization question, we do not know anything. So we can prove this with holes, it is NP hard, but without holes we do not have the reduction. And then the last open question is, say we have holes, but we do not allow Steiner points. Can you test, do you have any dynamic algorithms for both with general holes or point holes? So all these questions are open, and I will be really happy if someone comes up with some answers to these questions. And that is the presentation. Thank you for your kind attention. Thanks. Yes. Yes. So I told you that there is an approximation algorithm here for simple polygons. I do not know, maybe they also have for polygonal regions, but so far I remember you can approximate the Steiner points, and that is the log n approximation. And there they actually ask, can you, okay, so how they do it is you have pairs of points on the boundary and you want to find paths connecting those, but those paths have to be planar. So, this kind of finding paths, non-crossing paths, I forgot what they call this problem is, but it is also open. Can you solve that problem exactly? So, yeah, so there is this two related questions solving on probably would tell something about the other, but this is still on progress, like we don't know yet. Yeah. Yes.
So in your reduction, you argued that the clause used by Steiner point.
Yes.
I maybe it's asking for a figure you don't have, but do you have a picture of what such a triangulation actually looks like?
Okay, so I have something that would tell you something. So, I have some dents on the boundary of this polygon, right? And all of those dents have these tiny little lines, and you need one Steiner point over there, and some of them are crossing each other. So, putting one Steiner point somewhere will cover maybe 3 or 2. Yes, 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 and they are so tiny that putting one would cover at most 3. So, then we have a combinatorial graph where you can say that, okay, this graph has this matching property or covering property. So, you have the lower bound. Yes.